Hello everyone, we are from Group 6, and we will now talk about mathematics of cryptography. Primes and related congruence equations. We will first discuss about primes. How are prime numbers used in cryptography?
Prime numbers are used in cryptography because they are difficult to factorize. This means that it is difficult to find the prime factors of a composite number without knowing the factors to begin with. This makes it difficult for someone to intercept a message and read it without the proper key. Cryptography is all about number theory, and all integer numbers, except 0 and 1, are made up of primes, so you deal with primes a lot in number theory.
Prime numbers are numbers greater than 1.
They only have two factors, 1 and the number itself. This means these numbers cannot be divided by any number other than 1 and the number itself without leaving a remainder. More specifically, some important cryptographic algorithms such as RSA critically depend on the fact that prime factorization of large numbers takes a long time. Basically, you have a public key consisting of a product of two large primes used to encrypt a message, and a secret key consisting of those two primes used to decrypt the message. You can make the public key public, and everyone can use it to encrypt messages to you, but only you know the prime factors and can decrypt the messages. Everyone else would have to factor the number, which takes too long to be practical, given the current state of the art of number theory.
The sieve of Eratosthenes.
In 3rd century BCE, the Greek mathematician Eratosthenes found a very simple method of finding the prime numbers.
Follow the given steps to identify the prime numbers between 1 and 100. Step 1. Make 100 charts.
Step 2. Leave 1 as it is neither a prime number nor a composite number.
Step 3. Encircle 2 and cross out all its multiples as they are not prime.
Step 4. Encircle the next uncrossed number, which is 3, and cross out all its multiples. Ignore the previously crossed out numbers like 6, 12, 18, and so on. Step 5. Continue the process of encircling the next uncrossed number and crossing out its multiples till all the numbers in the table are either encircled or crossed out, except 1.
So, from the table 2 and 3 and 5 and 7 and 11 and 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53, 59, 61, 67, 71, 73, 79, 83, 89, 97 are the prime numbers. The special property of prime numbers. Every number can be factorized into its prime numbers.
Generally, it's very hard to find the factors of a number. To find all the prime factors of a natural number n, one has to try and divide it by its possible factors up to square root n. Although this approach is ineffective, it is a good place to start.
Euler's phi function. Euler's phi function is also called as Euler's totient function.
It can be used in the RSA encryption system, which can be used for security goals. The symbol used to indicate the function is phi, and it is also known as phi function. The Euler totient function phi n calculates the number of elements in z** operator n with the help of the following rules minus.
First rule. Phi of 1 equal to 0. Second rule.
Phi of p equal to p minus 1 if p is prime. For example, phi of 7 equal to 7 minus 1 where 7 is a prime.
Third rule. Phi of m into n equal to phi of m into phi of n if m and n are relatively prime.
For example, phi of 21 equal to phi of 3 into phi of 7, which is equal to 2 into 6 equals to 12 where 3 and 7 are relatively prime.
Fourth rule. Phi of p power e equal to p power e minus 1 where p is a prime.
For example, phi of 1000 equal to 2 to the power 3 into 5 to the power 3 equals to 400 where 2 and 5 are prime numbers. The following four rules can be combined to obtain the value of phi n. Factorize n as
n equals pe11 into pe22 so on pec.
The difficulty of finding phi n depends on the difficulty of finding the factorization of n.
Fermat's little theorem.
Fermat's little theorem states that if p is a prime number, then for any integer a, the number a power p minus a is an integer multiple of p.
Here p is a prime number. A power p congruent to a of mod p. Special case, if a is not divisible by p, Fermat's little theorem is equivalent to the statement that a power p minus 1 congruent to 1 of mod p here is not divisible by p. P equals an integer prime number. A equals an integer which is not multiple of p. For example, let a equals 2 and p equals 17. According to Fermat's little theorem, 2 power 17 minus 1 is equal to 1 mod of 17 is 65,536%, 17 equal to 1. That means 65,536 minus 1 is a multiple of 17. A primality test is an algorithm to decide whether an input number is prime.
There are the following types of primality testing, which are as follows. Deterministic algorithm minus a deterministic primality testing algorithm accepts an integer and continually output a prime or a composite. This algorithm always provides a proper answer. Divisibility test minus the simplest primality test is as follows minus. Given an input number n. Euler's theorem. Euler's theorem is a generalization of Fermat's little theorem handling with powers of integers modulo positive integers. It increases in applications of elementary number theory, such as the theoretical supporting structure for the RSA cryptosystem.
This theorem states that for every a and n that are relatively prime, a power phi of n equal to 1 of mod n,
where phi n is Euler's Totient function, which counts the number of positive integers less than n that are relatively prime to n. Probabilistic algorithm minus a probabilistic algorithm provide an answer that is correct most of time, but not all of the time. These tests decided whether n satisfies one or more conditions that all primes should satisfy.
Miller-Rabin is a fast approach to test primality of the large numbers.
This algorithm is called a Rabin-Miller primality test, and this algorithm decides whether number is prime, which is same to other tests. This test is based on equality or group of equalities that hold the true for prime values, thus checks whether they hold for the number that it is required to test for primality.
This algorithm is most useful known primality testing algorithm and can be used in different software libraries that based on RSA encryption, and best instance is OpenSSL.
Miller-Rabin validate that the number is composite.
So this is called compositeness test rather than primality test. The Miller-Rabin test identify all composites.
For each composite number n, there can be at least 3/4 Miller-Rabin of numbers are witnesses of compositeness of n. Miller-Rabin is associatively simple extension of Fermat's little theorem that enable us to test for primality with a much larger probability than Fermat's little theorem.
Here is the pseudocode for Miller-Rabin test. The following is an example. Apply Miller-Rabin algorithm using base 2 to test whether the number 341 is composite or not.
Solution: using Miller-Rabin algorithm, we can test the number 341 as follows minus. Advantages. This algorithm can be used to test high numbers for primality. Because of its advantage in speed when compared to other primality tests, Miller-Rabin test will be the test of choice for several cryptographic applications.
When compared to Euler tests, Miller-Rabin is more dynamic, and essential aspect is that the probability of failure is decreased.
According to the Fermat test, there are too many liars for all Carmichael numbers n. The error probability is near to 1. This disadvantage is prevented in Miller-Rabin.
Now we will discuss the factorization. Factorization, or integer factorization, is a commonly used mathematical problem often used to secure public key encryption systems.
A common practice is to use very large semi-primes, that is, the result of the multiplication of two prime numbers, as the number securing the encryption.
Fundamental theorem of arithmetic.
Every integer may first be factored as a product of primes in a unique way.
It must be stressed that the primes involved in a factorization are not necessarily distinct, as in 12 is equal to 2 times 2 by 3, and that we consider the same primes written in two different orders as the same factorization, that is, 30 is equal to 2 times 3 times 5 and 5 by 2 by 3 are considered to be the same factorization. The easiest canonical way to display n as a given product of primes is to write n equals p1 p2, pec for primes p1 p2 pk and positive integers e1 e2, ec. Trial division method. Below is the pseudocode for trial division method. The Chinese remainder theorem.
The Chinese remainder theorem is a theorem of number theory, which states that, if one knows the remainders of the division of an integer n by several integers,
then one can determine uniquely the remainder of the division of n by the product of these integers, under the condition that the divisors are pairwise coprime. The Chinese remainder theorem is widely used for computing with large integers, as it allows replacing a computation for which one knows a bound on the size of the result by several similar computations on small integers.
Theorem statement.
Let n1, nk be integers greater than 1, which are often called moduli or divisors.
Let us denote by n the product of the ni.
The Chinese remainder theorem asserts that if the ni are pairwise coprime, and if a1 ck are integers such that 0 less than or equal to ai ni for every I, then there is one and only one integer x, such that 0 less than or equal to x less than n and the remainder of the Euclidean division of x by ni's ai for every I. This may be restated as follows in term of congruences: if the ni are pairwise coprime, and if a1 ck are any integers, then there exists an integer x such that.
The solution is as below. CRT problem.
An old woman goes to market and a horse steps on her basket and crushes the eggs.
The writer offers to pay for the damages and asks her how many eggs she had brought.
She does not remember the exact number, but when she had taken them out 2 at a time, there was 1 egg left.
The same happened when she picked them out 3, 4, 5, and 6 at a time, but when she took them 7 at a time, they came out even. What is the smallest number of eggs she could have had?
This problem can be expressed as a system of congruences.
Application of Chinese.
In coding theory, detection and correction of errors is done by adding redundancy to data that is sent via a noisy channel or in a computer. The CRT remainder techniques are useful in developing code that detects errors. In cryptography, the CRT is used in secret sharing through error correcting code. The CRT is itself a secret sharing scheme without any need for modification.